Hi, welcome back to my class in Abstract Algebra. Today we will talk about isomorphism. We say that two groups are isomorphic if there exists an isomorphism from one group to another group. An isomorphism is a special type of homomorphism. And uh, An isomorphism is a homomorphism that is both an injection and a surjection. That is, an isomorphism is a bijection from one group to another group. A function from one group to another group that is both 1-1 or injective and onto or surjective is called bijective. And a bijective function from one group to another group is an isomorphism. Now, we state the 4 conditions to determine or test if the given mapping or function from one group to another group is a isomorphism. The first condition is we have to define a function from one group to another group. The first group has a binary operation defined on the non-empty set, and the second group has another or the same binary operation defined on the non-empty set of the second group. And we should define a mapping from the first group to the second group. The second condition is that we must verify that the operations of the two groups are preserved. That is, we verify the condition is stated in the definition of a homomorphism. The third is to verify if the mapping from one group to another group is a bijection. And this third condition is actually equivalent to two conditions. We must show that the given mapping is an injection, that is a 1-1 mapping, and the fourth is that the given mapping is a surjection or an onto function. And you recall from our set theory that a function is 1-1 if each element of the first non-empty set has a unique image in the second set known as the range or codomain of the function. And a given function is surjective or onto if each element of the codomain or the range is an image of at least one element in the domain or the first non-empty set. We now take some examples of how to show if the function defined from one group to another group is an isomorphism. Again, an isomorphism is a bijection from one group to another group that preserves the operations on the two groups. And if there exists an isomorphism from one group to another group, we say that the first group is isomorphic to the second group. we let R with the binary operation addition and set positive real numbers with operation multiplication be the two groups. And we define the function g or the mapping g from set R, the set of real numbers, to the set of positive real numbers by this: g of x equals 2 to the power x for every x element of R. We want to show that g is an isomorphism. And if we have shown that g is an isomorphism, we conclude that the set of real we will conclude that this group R is isomorphic to the set R plus, or the set of positive real numbers. Again, in checking or verifying whether one group is isomorphic to the other group is we have to define a function from the first non-empty set of the first group to the second non-empty set of the second group. But in this example, the function from set R to the set of positive real numbers is already given and is defined by this function g of x equals 2 to the power x for every x element of R. So we proceed with the second condition that must be verified to determine if G is an isomorphism, and that is we must verify that this function G defined preserves the group operations, or that is the condition stated in the definition of homomorphism is satisfied. From the definition of homomorphism, we must show that g of a plus b, the operation here is addition because the operation in the first group is multiplication. We must show that g of a plus b is equal to g of a multiplied by g of b. The operation at the right hand side is multiplication because the operation in the second group is multiplication on the set of positive real numbers. And this equation must be true for any two real numbers a, b, elements of the set R. A and b are elements of the set R because R is the domain of the function g defined or given. And we start with g of a plus b. Using the definition of the function g, where x now is a plus b, then g of a plus b is equal to 2 to the power a plus b. But by property of exponent, 2 to the power a plus b is equal to 2 to the power a multiplied by 2 to the power b. This property of exponent says that if you are multiplying expressions with the common base, here the common base is 2, you add the exponents. So 2 to the power a multiplied by 2 to the power b is equal to 2 to the power a plus b. But 2 to the power a is equal to g of a. Similarly, 2 to the power b, your x now is b, is equal to g of b. Therefore, we have verified the first property the property of homomorphism g of a plus b is equal to g of a multiplied by g of b. The next condition that we must show is that the function g is an injection. That is, g is both an... We must show that the second condition is that we must show that the function g is a bijection. That is, the function g is both an injection and surjection. G must be both 1, 1. We must show that g is 1, 1 and g is onto. We start by showing that g is an injection or a 1, 1 function. A function is 1, 1 if each element of the first set or domain R is assigned to unique image in the codomain of the function g. And if there are two images if two elements of the first set R have the same image in the codomain R plus, or the set of positive real numbers, then we must show that those two elements of R are equal and the same real numbers. And that's what we will do to show that G is a 1-1 function. We will take two elements of set R. We will take any two real numbers elements of the set of real numbers. And we will show that if these two elements of R have the same image, then those two elements of R are equal and the same real numbers. We want to show now that G is 1, 1 or an injection, or that G is an injective function. And we will do that as follows. We take any two real numbers in R, or the set of real numbers. Then we will show that if the image of A under the function G is equal to the image of B under the function G, then A and B must be equal and the same real numbers. That is, no two real numbers will have the same image if the function G is a 1-1 function or an injection. By the definition of the function G, the image of x under G is 2 to the power x. So the image of A under the function G, x now is A, G of A is equal to 2 to the power A. And 2 to the power A must be equal to the image of B under G. And by this function G, G of B, x now is B, is equal to 2 to the power B. And to eliminate the base 2, we take the natural logarithm of both sides to the base. We take the logarithm of both sides to base 2. And here we apply one of the properties of logarithm. You can also take the natural logarithm of both sides. Ln of 2 to the power a equals ln of 2 to the power b. If you take the natural logarithm of both sides, you get ln of 2 to the power a equals ln of 2 to the power b. But you can also do this, you take the logarithm to base 2 of both sides, because the logarithm of 2 to the base 2 is 1. But by property of logarithm, this is equal, the logarithm of 2 to the power a, the logarithm to the base 2 of 2 to the power a is equal to a times the logarithm of 2 to the base 2. By property of logarithm, the logarithm to the base 2 of 2 to the power a is equal to a times logarithm to the base 2 of 2. And it's equal to logarithm to the base 2 of 2 to the power b. Again, by property of logarithm, logarithm to base 2 of 2 to the power b is equal to b multiplied by logarithm to base 2 of 2. Now, the logarithm to base 2 of 2 is 1. But if you use ln or natural logarithm, you have to divide. This would be, if you use natural logarithm, this would become a times ln of 2 is equal to b multiplied by ln of 2. And you can divide both sides by ln of 2. Or here you can divide both sides by logarithm to base 2 of 2, and you will get a equals b. Thus, we have shown that g of a equals g of b implies if g of a equals g of b, we have shown that a equals b. That is, if two elements of the set of real numbers have the same image, then these two elements of the set of real numbers a and b must be equal and the same. That is, no two elements of the set of real numbers are assigned to the same image. Therefore, we conclude that the function g is injective or one-one function. And the third condition, we must show that g is a surjection or onto function. And to show that g is a surjection or an onto function, we must show that for every element of the codomain or the set of positive real numbers, each element of the codomain or the set of positive real number is an image of at least one element of the domain or the set of real numbers. We now show that the function g is an onto function from the set of real numbers R to the set of positive real numbers R plus, or we show that g is a surjective function, or g is a surjection from R to R plus. And we will show that for every element of the codomain R plus, there exists a real number element of the set R such that the image of this element of R is equal to that element of the codomain R plus. To show that the function is surjective, you start from the codomain or the second group, R plus. And you show that for every A element of R, or to each A element of R plus, there exists an element B element of the set of real numbers or the domain, such that the image of B, the element of R, is equal to A. This means that every A element of R is an image of some element B of the domain, the set of real numbers R. By the function defined by G, the image of B under G is equal to 2 to the power B. In the given function, we have g of x equals 2 to the power x, and we take x equals b. Therefore, g of b is equal to 2 to the power b and must be equal to a. And what we should do here is we must find this b element of real number. There exists a b element of real number such that g of b is equal to a. And g of b equals a implies that 2 to the b is equal to a. And from this equation, we solve for b by taking the logarithm of both sides to the base 2, by taking the logarithm to base 2 of both sides. And again, by property of logarithm, the logarithm to base 2 of 2 to the power b is equal to the exponent b times the logarithm to base 2 of 2 is equal to logarithm to base 2 of a. The safe logarithm to base 2 of 2 is 1. B times 1, b is equal to logarithm to base 2 of a. Now, a is a positive real number because we take that as element of R plus. So, a is a positive real number. And because it is a positive real number, the logarithm of a to base 2 or logarithm to base 2 of a exists. And it must be a real number element of the set of real numbers R. Therefore, we have shown that for every real number, positive real number, there exists a b element of the set of real numbers. There exists a real number b element of R, and b is given by logarithm to base 2 of a. So we conclude that the function g is 1, 1 or surjective. We conclude again from this result that the function g is onto, not 1, 1, onto or surjective. That is, the function g from set R of real numbers to set of positive real numbers is a surjection. And combining the results in parts 2 and 3 of this proof, we conclude that the function g is a bijection. Again, combining the results from parts 2 and 3. In part 2, we have shown that the function g is 1, 1 or an injection or an injective function. In part 3, we have shown that g is a non-2 function or a surjective function or a surjection. And combining the two results, we say that the function g is a bijective function that is both 1, 1 and on 2. And collecting all the three parts of the proof, we conclude therefore that g, the function from the set of real numbers to the set of positive real numbers, is an isomorphism. For our second example, consider the group consisting of the set of complex numbers under the binary operation addition of complex numbers. And we define the function f from the set of complex numbers to itself by this f of c is equal to z bar, where z bar here is the conjugate of the complex number z, element of the set of complex numbers c. And we want to show that the function f is an isomorphism. And this function f from the set of complex numbers to the set of complex numbers, if this is an isomorphism, is what is known as an automorphism. An automorphism is an isomorphism that is defined by a function from a group to the same group. As in function f defined from the set of complex numbers to the same set of complex numbers. And we verified the three properties. We skip the property that we define a function from the first group to the second group, because in this example the function is already defined. So we skip that condition and we proceed with the second condition. And we verify the property stated in the definition of homomorphism that preserves the operations on the group. For the first condition, we now verify the property in the definition of homomorphism. We take two elements of the set of complex numbers, the domain or the first set in the function f defined, and we denote these two complex numbers by z and z sub 1. And we show that f of z plus z sub 1, the operation addition is used at the left hand side because the given group consisting of the non-empty set has the binary operation addition of complex numbers. We show that f of z plus z sub 1 is equal to f of z plus f of z sub 1. Again, the operation addition is used at the right hand side of this equation because we have a function defined from set C to the same set C, or a function defined from the group of complex numbers under the binary operation addition to the same group of complex numbers under the same binary operation addition. And we start from the left hand side where z and z sub 1 are elements of the set of complex numbers, which means that these numbers z and z1 are numbers with imaginary parts and real parts of the following form. Because z and z sub 1 are elements of the set of complex numbers C, z is a number of the form a plus bi, where a is the real part of the complex number C and bi is the imaginary part of the complex number C, and I is equal to the root of negative 1. Similarly, because C1 is an element of the set of complex numbers C, C sub 1 is a number of this form, A1 plus B1I, where A1 is the real part of the complex number C sub 1, and B sub 1 is B sub 1I is the imaginary part of the complex number C sub 1, where I is equal to the root of negative 1. Now we find the function f of c plus c1, where the function f is defined as f of c equals the conjugate of c, where c is a complex number element of the set of complex numbers. So we start with f of c plus c1. We have f of c plus c1 under the function f defined is equal to the conjugate of c plus z1. And we obtain the sum c plus c1 the image of c plus c1 under the function f is equal to the conjugate of c plus c1, where the sum c plus c1 is equal to quantity a plus bi. This is the complex number c plus the complex number c1 equals a1 plus b1i. And we collect the real parts. A and a1 are real parts. And we collect the imaginary parts, bi plus b1i. And you can see that I is a common factor, so we factor I to the right. Thus, the sum of the complex numbers c and c1 denoted by c plus c1 is equal to quantity a plus a1 plus quantity b plus b1i, where the real part is the sum of the real numbers a plus a1, and the imaginary part is quantity b plus b1 multiplied by I. Now we can take the conjugate of c plus c1, which is equal to this, and the conjugate of the complex number is obtained by getting the opposite side of the imaginary part. In the sum c plus c1, the imaginary part is positive quantity b plus b1i. So the conjugate of c plus c1 is quantity a plus a1 minus, we simply take the opposite sign of the imaginary part of the complex number, minus quantity b plus b1i. Thus, f of c plus c1 is equal to conjugate of c plus c1, where c plus c1 is equal to this complex number, and its conjugate is obtained by changing positive to negative. And from this, we distribute negative and I negative from the left and I from the right. And we remove the grouping symbols A plus A1 minus B1I. We distribute negative from the left and I from the right. Negative B multiplied by I. Negative B1 multiplied by I. Now we collect the terms without the subscript 1. We have A minus BI. And we collect the terms with subscript 1, quantity A1 minus B1I. But our complex number C equal to A plus BI, its conjugate denoted by Z bar is A minus BI. So A minus BI here is the conjugate of the complex number C denoted by Z bar. Plus A1 minus B1I is the conjugate of the complex number C1, denoted by Z1 bar. C1 bar is the conjugate of C1 obtained by taking the opposite sign of the imaginary part of C1. Hence, A1 minus B1I is the conjugate of C1, denoted by Z1 bar. But Z bar, the conjugate of C, is the image of Z under the function f. And Z1 bar is the image of Z, complex number Z1 under the function f. That is, f of C is equal to Z1, Z bar. F of C sub 1 is equal to Z sub 1 bar. Thus, we have shown that f of C plus C1 is equal to f of C plus f of C1, which is this equation that we want to show. Therefore, the first condition, the property of stated in the definition of homomorphism, is satisfied by the function f. Now we show that the function f is a bijective function, that is, it is both f is both on 1 and on 2. We now show that the given function f from the set of complex numbers to itself is a bijective function, and we start by showing that f is a 1-1 function or injective function. And as we did earlier, we take two elements from the set of complex numbers and we assume that these two complex numbers elements of C, the set of complex numbers, have the same image. Then this would imply that the two complex numbers elements of set C, the set of complex numbers, are the same and equal complex numbers. We now show that f is 1-1 or injective function. we let C and C sub 1 be any two elements of the set of complex numbers C. Then if f of C, the image of C under f is equal to f of C1, the image of C sub 1 under the function f are equal, then we must show that C is equal to C sub 1. That is, the two complex numbers C and C sub 1 with the same image, equal image, are the same and equal complex numbers. And then we will conclude that f is 1, 1 or injective. That means that the image of each element of the set of complex numbers is unique, which implies that if two elements of the set of complex numbers have the same image, that is, their image is not unique, then these two, and the function f is 1, 1, then these two complex numbers must be the same and equal complex numbers. And we start from the left-hand side under the function f of C defined earlier. F of C is equal to the conjugate of C denoted by C bar. But first we let C be equal to A plus BI because C is an element of the set C of complex numbers, so C is a number of the form A plus BI. Because C is element of C, C is a complex number of the form A plus BI, and similarly C1 is element of C, so C sub 1 is a complex number of the form A1 plus B1I. Now we find this equation, the value f of C equals f of C1 implies that f of C is equal to C bar. By definition of the function f earlier. And f of C1 is equal to the conjugate of C1 denoted by C sub 1 bar. But C bar is the conjugate of the complex number C obtained by taking the opposite sign of the imaginary part of C. So C bar is equal to A minus BI. And C sub 1 bar is the conjugate of the complex number C given by A1 plus B1I, and C sub 1 bar is obtained by taking the opposite sign of C sub 1. The C sub 1 bar is equal to A sub 1 minus B sub 1 I. And this equation will be true only if the real parts of the complex number at the left is equal to the real part of the complex number at the right hand side. This means that A minus BI equals A1 minus B1I implies that A is equal to A1. This equality implies that the real parts are equal. A equals A1. And the imaginary part without the negative sign, B sub I, must be equal to B sub 1I. Only if these are true that this equation will be true. If a sub 1 is equal to a, then the complex number c sub 1 will become a plus b sub 1 I is equal to b sub b I. Therefore, the complex number c1 is equal to a plus bi, which is equal to the complex number c. Thus, we have shown that if f of c is equal to f of c sub 1, this implies that c is equal to c sub 1. And we have shown that f is a 1-1 function or injective function, because we have shown that if there are two elements of the set of complex numbers c and they have the same image under the function f, then these two complex numbers elements of the set C of complex numbers must be the same and equal complex numbers. We therefore conclude that the function f is 1-1 injective, because we have shown that if f of c equals f of c sub 1 for complex number c, c sub 1 elements of the set of complex number c, we have shown that c is equal to c sub 1. And the last part of the proof, we showed that the function f is onto. And to show that f is onto or surjective, we start from the codomain, but the codomain of f is the same complex number c. We show that for every element of the set of complex number c, there is at least one element in the set of complex number c also, whose image is equal to that element of the set of complex number c. We showed that g is onto or is a surjective function from c to c, and we do that by showing that for every c sub 1 element of c, this is the codomain c, there fc is a complex number c element of c also, the domain is also c, such that the image of this complex number c under the function f, such that the image of the complex number c under the function f is equal to c sub 1. And again, we write c as a complex number of the form a plus bi. Because c is an element of the set of complex number, it is a number of the form a plus bi. So f of c is equal to, by the function defined f earlier, is equal to the conjugate of c. And the conjugate of C, it since the complex number A plus BI is obtained by taking the opposite side of the imaginary part of C. So C bar is equal to A minus BI. Also, we let C be equal to A1 plus B1I because C sub 1 is an element of the set of complex numbers. So C sub 1 is a number of the form A1 plus B1I. And C sub 1 must be equal to f of C. And f of C is equal to A minus BI. F of C is equal to A minus BI. And it is equal to C1. And C1 we let as A1 plus B1I. We are looking here for a complex number C. The given here is the complex number C sub 1. We start with the complex number C sub 1 for every C sub 1 that exists a C. So we are looking for a complex number C whose image is equal to C sub 1. And so we solve from this equation for A and B. And this equation will be true if this complex number is equal to this complex number at the right. And these two complex numbers will be equal if their imaginary parts are equal. And that's the only way that these two complex numbers will be equal. Their imaginary parts are equal. Minus BI is equal to B1I. And their real parts are also equal. A1 is equal to A. Thus, A minus BI equals A1 plus B1I implies that A is equal to A1. And minus BI is equal to B1I. This implies that A equals A1 and multiplying both sides by negative. Negative multiplied by BI is positive BI equals multiplying the right hand side by negative. Negative times positive B1I is negative B1I. Hence, the complex number Z, which is equal to A plus BI, is equal to A1 plus BI. BI is minus B1I. We have shown that for every C sub 1 element of C sub 1 is a complex number of the form A1 plus B1I. There exists a complex number C, element of C, and this complex number C we have shown is equal to A1 minus B1I, and we are sure that this complex number exists because A1 and B1I are the real part and imaginary parts respectively of the complex number C sub 1. And you can check that f of C is equal to C1. F of C is the conjugate of C. And the conjugate of C is A1 plus B1I, which is equal to C sub 1. So this condition is satisfied. Therefore, we have shown that the function G is onto or is a surjective function or a surjection from the set C of complex numbers to itself. And combining the two results, the results in parts 2 and 3, we have shown that the function is f. We have shown in part 2 that the function f is 1, 1 or is an injection. And in part 3, we have shown that the function f is onto function or is a surjection. And combining the results in parts 2 and 3, we say that the function f is a bijective function or is a bijection from C to itself. And combining all the three results from parts 1 to 3, we conclude that f is an automorphism. An automorphism is an isomorphism from a group to itself. We now construct an isomorphism between two groups, and each group has a non-empty set of order 2. We start with group G under the binary operation star, and G consists of a non-empty set of order 2, which means that the non-empty set of set G has only two elements, and one of these elements must be the identity element, because one of the properties of a group is the existence of identity element. And if the non-empty set is a set of order 2, then the other two element is a non-identity element. And we denote this non-identity element by small a. We let G with binary operation star be a group where G is a non-empty set of order 2 because G has two elements, and one of the elements is the identity element denoted by E, and the other element is the non-identity element. We construct a table for group G under the binary operation star. Because E is the identity element, if we combine E with any other elements of G by the binary operation star, the answer is that element of G. Hence, E star E is equal to E. E star A is equal to A. And E star E equals E, the identity element. E star A must be equal to A. And each element of G must appear exactly once in any row or any column. Hence, in this cell, we must write E. This table shows the structure of the group G under the binary operation star. Now we define another group, C sub 2. We let C2 with addition modulo 2 as the binary operation on C2. And as we have defined in the previous lesson, C2 is the set of integers from 0 up to n minus 1, where n here in C2 is 2. Therefore, the elements of C2 are the integers 0 to 1, where 0 is the identity element under addition modulo 2. And again, we construct the table to show the structure of this group C2 under binary operation addition modulo 2. We have 0 plus 0 under addition modulo 2 is equal to 0. And 0 plus 1 under addition modulo 2 is 1. 0 plus 1 under addition modulo 2 is 1. And 1 plus 1 under addition modulo 2 is 0. Now, as I said, we will construct an isomorphism between these two groups. And we denote that isomorphism by function f from the set G to the set C2. Now, the function f from set G to set C sub 2 is an isomorphism. If the function f is defined as follows, f of e is equal to 0, f of a is equal to 1. You can see that the image of each element of G is unique. Therefore, f is 1, 1. The image of e is 0, unique, and 0 is in the codomain of f or C sub 2. The image of a element of G is unique. It is 1, only one image, and 1 is element of the codomain of f, C sub 2. So the function f is 1, 1. And each element of C2, 0 and 1 is an image of an element in G. 0, start with 0. 0 is an image of element E under the function f. And 1 is also an image of an element A of the non-empty set G. Therefore, the function f is onto. And you can see from these two tables that if the binary operation the binary operation addition modulo 2 is replaced by the binary operation star, and 0 is replaced with the identity element E of G, and one element of C2 is replaced with the element A of G, the resulting table would be this table. Similarly, if in this table the binary operation star is replaced with addition modulo 2 and the identity element is replaced with the identity element 0 and A is replaced with 1, the resulting table would be this table. That means that goes to show that the structure of the two groups are essentially the same. That is, the group G and the group C2 have the same structure, or they are essentially the same, but technically they are different groups because they consist of different non-empty sets and they have different binary operation, but their structures are the same. The structure of this group G can be obtained from the structure of this group C2, and vice versa, the table for group G can be obtained from the table of C2 because they have the same structure. And for that, we conclude that there is a unique group of order 2 up to isomorphism. We cannot say that that is, there is only one group. There is essentially only one group of order 2. You can only form one group with non-empty set consisting of two elements, that is a unique group of order 2 up to isomorphism. That means that all the groups consisting of non-empty sets of order 2 are essentially the same. They have the same structure. And we say that there is a unique group of order 2 up to isomorphism. In mathematics, we refrain from saying the same because these two groups, as you can see, are not exactly the same. They are technically different groups, but they have the same structure. So we say that there is a unique group of order 2 up to isomorphism. For your practice, please try the following exercises. Number 1, let n be an element of the set of positive integer. So small n here can be any positive integer or any counting number from 1 up to positive infinity. Show that this group NZ, the set NZ is obtained by multiplying the set of integers, the negative integers, the 0 and the positive integers, by the positive integer n element of C+. Under the binary operation addition, this is a group. Show that this group and this group, the set of integers, under the binary operation addition are isomorphic. That is, you show that this function f from z to nz is an isomorphism, and the function f is defined by f of x equals nx for every x element of C. Number 2, show that the function g from the set R of real numbers to the set of positive real numbers, we had the same isomorphism earlier from set R to R plus, the set of positive real numbers. Show that this is an isomorphism from this group of real numbers under the operation addition to this group of positive real numbers under the binary operation multiplication, defined by g of x equals a to the power x for every x element of R, and a, the base a here, is not equal to 0 and a is not equal to 1. Number 3, show that there is unique group of order 3 up to isomorphism, like what I did in the last example. To show that there is a unique group of order 2 up to isomorphism, I constructed two groups. The first group consists of the non-empty set with two elements because the group has order 2, and the two elements of G are E, the identity element, and another element A, which is a non-identity element. And the binary operation star, I constructed a table for that non-empty set G with two elements under the binary operation star. And I constructed another group, Z2. Now for your assignment, you construct the second group, Z sub 3, with elements from 0 to n minus 1, where n is 3. and the binary operation is addition modulo 3. And you show that the tables of these two groups have the same structure, or one table can be obtained from the other table and vice versa. And you conclude that there is only one group of order 3 up to isomorphism, which means that all the structures of this group with non-empty sets of order 3 are essentially the same. The structures are essentially the same, but technically these groups are not the same because their non-empty sets consist of different elements and they have different binary operations, but it is the structure of these groups that are the same. So you show that there is a unique group of order 3 up to isomorphism. And that completes our lesson for today on isomorphism. And we will take some properties of isomorphism in the next lesson and the invariant properties under isomorphism. If you have questions about the lesson today, please ask your questions in the comments below. And thank you for joining me in my class today in abstract algebra.